Everybody. So I'm going to talk about the project entitled Machine Learning Approach for Argo Data Quality Control. This was done by Marnoush, Rock, who's online and was coming virtual, and me and Tobias, our mentor. So just to introduce what's Argo data, of course everybody knows, but so it's a global array of over 3,000 free drifting floats, which measures temperature, salinity, and currents for the upper 2,000 meters of the ocean. If you can see, the deployment is here, and then it goes down to deep and collects data, and then each 10 days when it comes up, it transmits the data, and with which we have a profile of temperature and salinity, and it covers almost all the regions of the ocean. So the project goal was to add another venue to the quality control of Argo data using machine learning. And why is that important? Because ocean environment is harsh, so there might be unpredictable errors in the Argo data, and people rely on that. And actually, inaccurate data leads to incorrect conclusions about oceanic and climate processes. So it's important to make sure that the data is correct, and also it's important to be proactive in correcting or discarding these inaccurate data, because it will be resource intensive if we do it afterwards. So just to review, we're going into the details, but the procedure was this. So we got the data from the GDAC, and which is the Global Data Assembly Center, for 1 year of temperature and salinity as variables, and the region was North Atlantic, and so then we tried to. The next step was to prepare the data for the machine learning model. We used an unsupervised Gaussian mixture model, and then we had the trained machine learning model, and the results were first 7 covalently structured regions of temperature and 3 for salinity, and then we have quality control profiles and also polygons. Both do the same thing, but polygons are easier to work with. And then also we use some spike data for performance check to see if the model works good or not. So, Merge, can you continue?
Yeah, thanks. To have the proper data of the Argo, we use the Argo Python package to get the 1 year of the Argo data, and we consider the 2,000 meters depth to make sure that we surpass the thermocline in the selected region. And the region we can see there, we selected the small region, but the data was big. We did some interpolation in the data because of 2 reasons. Firstly, we wanted to have evenly spaced pressure levels. Also, we have some NAND data in Argo data, so we did some interpolation to put almost accurate data instead of NANDs. That's the data we use for the machine learning part.
Yep. So, and then the next step was the model. So the Gaussian mixture model is the model which estimates actually the probability density function of a set of data set, and then groups the data together based on how much they are similar to each of those probability density profiles. And then so yeah, here you can show that each group, basically it's showing the groupings of data which are similar to each of the Gaussian distributions. And the model that we use, the algorithm that we use is PCA. I guess Philippe talked about, but basically it actually identifies the principal components based on of a data set, and then it helps reducing the complexity of working with a large amount of data, and we improve the speed. So instead of working with 2,000 variables, we can only work with 7 variables, which are the principal variables of a data set, and with that we can capture almost 99% of the covariance of the data. And Okay, so with the results, I would say, so here, basically you can see the solid lines. Look at the solid lines. These are the 7 classes of profiles that we got from the data that we had, and the solid lines are the mean values, and the dashed lines are the I mean, basically they're showing the range that we would if a data fits within this range. For example, here we would tag that the data to be good, and if it falls out of this range, we would say the data is bad. I mean, actually, it's not. We're not saying that the data is bad. It's like we have to check whether the data is correct or not. Same thing happens for the salinity, but actually, if you can see, we have 3 classes of 3 classes, which means we suspect that this method works very well for the salinity. Maybe it works better for temperature, but we have to investigate more in depth. Actually, the number of classes, we tried to see how many principal components cover the 99% of the data, and for salinity it's 3, for temperature it's 7. Yeah, and also this is the interesting part, I would say. So here you can see this is the map. This is the map, and here this is the region that we work with. And you can see we didn't train the model with the latitude and longitude, but it gives us like a classification of the regions based on their temperature profile, which is impressive because you can see there's a green region here with different profile and yeah, different regions, and also with salinity. I think this is really intuitive, but we have to dig into it. And the next step was to see how's the performance of the model. So Rob, I guess, can continue on this. Rob, are you?
Yep, I'm here. Thank you. So I think in an ideal world, you know, we would have liked to look at known bad data in the real world, but given we had a limited time,
1 minute.
we knew we would be spending all our time doing that. So instead, we basically introduced spikes ourselves, just using a normally distributed random data set, just to add some noise to the data and see how the model did. We also wanted to compare that to known quality control, like existing quality control. In this case, we used the IUS spike tests. Anyone who's unaware, that's NOAA's integrated ocean observing system. They have a number of QC tests. In this case, we ran the spike test, which is looking data point to data point for spikes at a defined threshold. And you can see here on the left is the IUS, and on the right is our model. It's kind of difficult to see with the IUS, but there are a number of single points that it flagged, but it didn't specifically flag the circled area, which our model did. And I believe the reason for this is the IUS QC test is looking data point to data point within a profile, while our model is kind of looking in a more holistic way. So you can kind of see how our model does present a different look than existing QC methods. So we thought this was, you know, an effective test to say, hey, are we adding, you know, value over existing QC? And I think, you know, given more time, we could look at other tests as well. And I believe I'm passing it back for the conclusion.
Yeah. So for the conclusion, as I said, I think machine learning is a new approach to quality control Argo data. It's we have to add this. We're not saying that the other methods are ineffective, but so the unsupervised gas mixture model, it classifies regions of similar temperature and salinity profiles, and this model works better for temperature rather than salinity. And actually, there are a lot of very recent works on this topic. We started figuring out new and newer papers as we went through. So it is. I guess it's very interesting to look into more in depth. And our next steps would be, so we need to apply the model for a longer period to see if the model is if we can see any improvement. And also we can apply the model on different regions rather than only North Atlantic. And also there are some changes in the temperature profile or salinity profile because of the change in the season. And it's important to see what happens if we include the seasonality in our data. And also we have to investigate the performance of our model with real bad data, because here we added some specs to test the model, but it would be interesting to see what happens if we have real bad data. So with this, I will stop here and thank you. We're open to questions.
Thank you. Do we have any questions?
Can I just say, if anyone in the room is asking a question, can you project your voice loudly as if you're speaking to the owl and everyone online, because they can't hear questions from the room. So if you just speak quietly, can someone repeat the question loudly near the microphone?
I don't have a question, but I do have a comment. So we have been doing something like really similar to apply the GMM, our like CTT data profiles in our archive starting from 1930s. In a larger region, like the entire Pacific region plus Arctic, we do enter a lot of like problems to like a lot of things to look into, but it's really useful. For us, we kind of like apply this to look for the anomalies, the detect anomalies in the like long-term data archive.
Thank you.
Okay.